department. If you look at the area with the CIEM, that is our department on Center for Integrated and Emergency Management, and we are working in collaboration with that for disaster response. As other topics are also included, this is one of the topic which is related to CIEM. So, if we look at the top two images, we can see which one is a fire in a forest and which one is not a fire. So, silly question from my side. It's looking very straightforward. The left one is a fire and right one is just a sunset. But the real challenge is, if we have a forest fire or a wildfire, then we need our UAVs are drawn to make it understand which one is a fire and which one is not fire, depending upon the environmental conditions. That could be based upon some sunlight reflections, fog or dust, or any kind of conditions. So we have to identify the origination of a fire, and we have to mitigate the problem as soon as possible through UAVs, so that we can avoid the spread of the fire in a wild forest. So for this problem, there are a lot of recent works which are presented, and from 2021 to 23-24, these are four of the top algorithms which were presented. Convolutional neural network with LSTM, faster RCNN, and improved version of YOLO V5 was presented for the fire detection using remote imagery or UAV imagery sensors. So, as I already said, we have to detect the fire, then we have to inform the first responders or the emergency institutions, so that they can take the mitigations as soon as possible. But the real challenge is to detect the fire in a diverse conditions. And when we are talking about UAVs and talking about drones, then we have a very limited computational resources. So we have to make deep learning models which are highly efficient, lightweight, which can increase the detection time and has less computational power, which we can deploy in a real time on a UAVs, and it can be used effectively with higher accuracy. So before going into the technique, this is a challenge currently, that we don't have that much standard publicly available data sets on remote imagery or UAV images for the fire detection. So there are some of the well-known publicly available data sets which are available, which we can use. So this is the one of them which I have already provided the reference, and it is also in a paper. So we have used these data sets which have 950 images which are evenly divided between fire and non-fire, and this is our training, testing and validation split for the fire and non-fire detection. So in the proposed technique, we try to use the expertise or the capabilities of an inception module with the residual module for our fire detection. So that is the hybrid model, which is a combination of an inception module which is inside, which is basically a combination of a convolutional multiple convolutional layers, which helps us to extract the features diversely, and then using the residual module, which gives us depth into the model, and it helps us to understand the different features of the figures of the image for the fire detection. And as compared to ReLU, we have tried to use hard switch activation function, which really helps us to avoid some of the problems which are built in with the ReLU function. Some hard switch activation function, some introduces some smoothness and no linear transition around the zero, as we have seen in the previous figure. And the one of the issue with the ReLU is the dying ReLU, which hard switch still outputs give us some small non-zero values. So this activation function really helps us to get the features and get the decision in a better way as compared to the ReLU function. So as I discussed at the start, there was some state of the art which were presented, and we have done the comparative analysis. As we can see in a table, some of the state of the art, we have done comparative analysis. And as I mentioned at the start, our challenge was to make an algorithm which is computationally less expensive as compared to the previous one. So before going to accuracy and everything, second last column, which is the parameters. So the proposed model which we achieve have around 5 times or 10 times less parameters as compared to the state of the art algorithms. We have less detection time, and also we are having the better accuracy, precision and recall in terms of ROC and configuration metrics also. So this is a broad comparative analysis with the state of the art which we have done and presented. I will not say it's a fully explainable, but to add some kind of explainability into our model, we have used a GradCam method to just visualize that how the model is understanding and extracting the features for fire and non-fire figures for the classification. So this is just a comparison of how the model is understanding between the fire image and the non-fire image. So in the future work which we have already done, so I think it's really worth it if I mention it. So as I mentioned, we have only tested and trained this work on a one data set. Then we have updated the model and we have worked on it, and for better generalizability we have used another data set for the fire detection, and we have done training on dataset 1, and then we have tested on dataset 2, and then we have trained on dataset 2, and then we have tested on dataset 1. We have also tried to apply the quantization to make it less computationally expensive in terms of weights values, and right now this work is undergoing activity transactions on geoscience and remote sensing. Thank you so much. This is all from my side.